Thank you. Thanks for the intro. I hope everyone can hear me, and it's good to see that no one is leaving after you said that no pizzas are coming later. So thanks for staying. Right. So my name is Nikita, and a few words about me. I work as applied scientist at AWS, where I am building and developing ML solutions for different use cases. And in the previous 5 years, I have spent quite a lot of time on Kaggle, doing many different competitions. I took part in more than 20 different competitions and was able to reach the medal zone in 18 of them. So this is why I'm going to talk about some of the experience that I earned during that time. And to talk a bit more about the team I'm working with at AWS. What we do is we work with different external customers, so mostly companies, and we try to help them identify the high-value use cases where machine learning could help, and then we go and build proof-of-concept solutions where the business problem that the customer has can be solved by machine learning. And as part of the science team, I am usually responsible for building these models and developing the solutions that work across different industries. So the kind of work that I do at AWS also resembles the Kaggle competition format to some extent, because you have to work on different projects in different domains, and you have to transfer some knowledge you learn along the way. So today I'm going to talk about a couple of lessons from Kaggle competitions and from competitive ML in general. First, I'll start by saying a few words why I think it is important and why are we talking about this today. And then I'll go through 3 lessons. I will not dive too deep into fine-tuning a specific algorithm for a specific use case, because I don't think that this would bring the best value to most of you who sit here today. I'll try to stay relatively high level and work through different lessons on different stages of machine learning project. All right. So first, let me start by saying why I think it is important to talk about lessons from Kaggle and competitive ML in general. So I'm sure that most of you are familiar with Kaggle, and if you are not, what Kaggle is, this is one of the online platforms where people compete, where data scientists compete solving different machine learning problems. You can find data sets, you can find tutorials on Kaggle, but the thing it is known for is machine learning competitions. And in the previous year, there were more than 10 million registered users on this platform. And if you look at a typical Kaggle competition, this is a leaderboard from one of the competitions where participants are judged by a specific score, by a specific model accuracy metric. You will see that the average difference between teams that are competing tends to be very small. And that basically means that when thousands of people compete, they have to come up with a series of special best practices or lessons learned in order to really beat the others, succeeding in this very minor increases of a specific evaluation metric. And this is why we can learn from these lessons and maybe try applying them in some of our projects as well. So some of these lessons are very specific, but some of them can be used in the industry as well. And today I'm going to talk about some of them that I feel would be useful for other projects. So let me start with the first thing. The first lesson is about compressing your data. Now, if we look at the landscape of previous competitions in 2022, you will see that for some competitions, the dataset size tends to be quite big. There is a big number of competitions where data size is bigger than 1 gigabyte, and then there are some competitions where the size goes even beyond that. And although in some cases this is related to the fact that there is unstructured data, images, videos, something else, but even with tabular data, you can see that in some of the previous competitions, so this is a competition that was running on Kaggle 9 months ago, the data size can go up to 50 gigabytes with the tabular data as well. And the tabular use case is something I want to focus on today, because in many of the industries, in many of the use cases, we are working with tabular data. And we have to know how to work with the data sets that are so big. And the problem that we face here is that sometimes as data scientists, we want to import the data and we want to do some modeling, but sometimes this data is too big. So we want to do something about that. We don't want to use a very large compute instance because we don't want to spend additional money on having to employ these instances. Or sometimes we don't even have access to compute resources that support such high dataset sizes that we need to fit in our memory. So what we can do about that is that we can actually compress the data using the lossless compression. So I'm talking about the kind of compression where we are not losing any information that is stored inside of the data. And this is something that you can see people using on Kaggle in tabular data competitions. The benefit of that is that we can save costs on the running, on the compute instances that we need to use, and we can also improve the speed of experimentation, because if we, in a given amount of time, can actually use a smaller instance and do faster operations, faster data processing, faster feature engineering, we can do a bigger number of experiments as well and benefit from that. So the main idea of the lossless data compression is to actually go and look more closely at the format of the variables that we have in our data set, to look at the variables and see whether we can change this format in such a way that we can optimize, reduce the size that the data takes into our memory, but still maintains all the information that is needed. Let me give you an example. Let's say we are working on a demand forecasting use case. We are predicting how we are selling the items. And one of the variables we have is the number of previous orders. Well, first of all, we know that the number of previous orders shouldn't be a float. It is an integer. You cannot have 2.5 orders. You can have 2 or 3 previous orders. And then depending on the company that we are looking at, depending on our market size, we can figure out that the maximum number of orders that a person has in the data set will probably not exceed, let's say, 32,767, which is the range that the 16-bit integer has. When we input the data by default, most likely what we will use for storing the number of purchases as a variable, we will use integer 32 or float 32, because this is what one of the data processing libraries, such as pandas, will select for us by default. By leveraging the knowledge and knowing that we will not exceed a certain number, we can actually overwrite the format of that variable and say this is going to be integer 16. That way we are saving some space that this variable takes into the memory, and we are improving the overall size of the data set that we will going to use. In one of the previous projects that I have been doing at work, we were able to increase the size of the data sets of one of the data sets that we worked with from 1.6 gigabytes to 0.2 gigabytes without losing any information. So you see it's 85% reduction without losing any information. And of course, in that case, we are able to fit much more information into the remaining RAM. We are going to go for a lower instance that doesn't require a lot of cost, and we are going to be faster when doing experiments. So whenever you work with tabular data, you can do the compression before you actually start the modeling and save some time and save some costs here. Looking at the unstructured data, I know we talked about the tabular data now, but you might be wondering, okay, but what if I am working with images? Well, if you work with images, there is no way to really do the lossless compression as in the tabular data use case. But one thing that people do frequently on Kaggle is to do the so-called gradual increase of the image size when you do the training. So this happens not on the data import stage, but this happens on the model training stage, where instead of starting right away with images that have very high resolution, you can start with low resolution first. So maybe the first couple of epochs you are training with an image size that is actually small, 128 by 128, for example. And then after a certain number of epochs, you switch to a larger model with a larger, to a larger image size, but using the same model and using the weights that you have fine-tuned from the previous 3 epochs that were running on a smaller image size. And that way you can gradually increase the size, and the first epochs that you will be training the model for will take much less time compared to starting the training right away with a very large instance. Okay, so let's say we did the data compression. We are now going to think about how do we split the data to do the training and validation and to evaluate our models. The training validation and the designing of the good validation strategy is probably the most important thing that happens on Kaggle in general. Because what you will typically see in many of the Kaggle competitions, you will see that there is a public leaderboard that is available to participants beforehand, and then there is also a private leaderboard on which the participants are evaluated after the competition is finished. And since this leaderboard, this test set is hidden from the participants from the very beginning, what frequently happens is that a lot of teams overfit to the public validation set that has been available. And then once the competition ends, the top people that you see on the public leaderboard are completely different from the top people that you see on the private leaderboard. This is a so-called shake-up in the Kaggle terms. This can happen in Kaggle, but this can also happen in the industry. So let's say that we are a company that sells products in market A, and we are now entering market B, which has slightly different properties, which has slightly different distribution of the data. What we can sometimes observe that if our training data, our historical data is coming from market A, and we train and validate our model on that, that once we see a very good performance of the model offline on this previous historical data, then we go to the market B and realize that our model is not doing any well. Realize that we have a sudden drop in the model accuracy. So we have this shake-up as well. So the question is, what do we do with this problem, right? We want to have offline performance consistent with online performance when we go and implement our model in production, whether it's a new market or simply a new sample of people coming in and buying our products next week. And the idea here, in general, is to set up a validation set that mimics the production environment as close as possible. Now, there are many tricks and tips how to do that specifically, but the main topic is let us try to design a validation set that is as close as possible to what we expect to see in production. And I put a couple of things here on the slide that represent things that you could start with when going here. But please know that this is a big space of different opportunities, and there are many things to explore here. The first thing to start with is, of course, to do the stratification whenever you split the data into a training and validation subset. For those of you who are not familiar with what stratification means, it basically refers to the fact that we are aiming at keeping the same proportion of a specific variable in the training and in the validation. So let's say if our training set has a proportion of returning customers 30%, we want to have the same proportion in the validation data so that we are not changing the distribution too much. I think many people go with stratified split when talking about binary or categorical variables, but not many people know that we can actually use that with continuous variables as well. So what you can see people doing on Kaggle is actually, if you have a lot of continuous variables, not necessarily only the target variable, you can actually bin them. So let's say, giving a number of previous purchases, we bin them in different groups, from 0 to 5, from 5 to 10, from 10 to 20, and so on. And then we can stratify based on the proportion of this created categorical variable. That way, we have a slightly different data distribution in the sense that we are not looking at each unique value of this continuous feature, but we're still representing and catching the overall shape of the distribution and ensure that it is similar enough in our training and validation sets. Another thing that is very important in the industry is to actually regularly update the data partitioning in the anticipation of the distribution shifts. This is not something that happened on Kaggle, even though even on Kaggle, you have to periodically update your train validation split if you want to avoid overfitting to that too much. But what happens in practice is that the customers that come to your company next week may be coming from a slightly different area of the data distribution. And you want your validation sample to match that data from that distribution. And then you want to take this data, you want to take data from the customers that come the last week, And even if your historical data from the last year tells you that the proportion of returning customers is 20%, you want to match the proportion that comes from the last week. So if the last week it is 50%, then you want to match this proportion, because this is the data distribution you are optimizing towards. And then one of my favorite things that is learned from Kaggle, but is also very suitable in many of the projects when you have to do the data validation, is actually the so-called adversarial validation. What you can do is you can actually check the quality of your data split. And how to do that? So let us take this data from the last week, from the customers that came to us and bought something last week, and let us take our validation set that we built from the previous historical data. What we can do, we can mix these two samples together and train a model that tries to distinguish whether the data comes from the validation set or from the production sample from the last week. And if the model will be able to distinguish those data sets pretty clearly, it means that we have a bad validation. It means that we have a bad split because our data samples are different. But if our model trained to distinguish the two samples has an accuracy of about 50%, so close to random, then we know, okay, our split seems to be doing a good job in the sense that our training and validation samples are very similar. Good. Let me move on to the next stage. So let's say we compressed our data, then we defined the training validation split. Now we want to start training models, and we want to know which metric do we want to use to train and evaluate our models. And this is something that is learned on Kaggle because there is only a specific evaluation criteria on which your team will be evaluated. So if you have accuracy of 99%, but the competition metric is precision, no one will care about having such a good accuracy. You should only care about precision. How it works in business is that we as data scientists usually look at many statistical metrics, root mean squared error, recall, precision, some other things that we are used to, that we optimize, but what our model is evaluated on is some business KPI that will in the end be used to make a decision whether the model is doing any good, whether the model should be deployed to use for this specific business problem. And what I'm trying to say here is that this business KPI should also be the metric that should guide each of the modeling decisions that you make along the way, starting with training your model and then going to all of the stages of the model selection and optimization. A good example is a demand forecasting use case where the costs of over-predicting and under-predicting are actually not the same. Because if you over-predict and say that this item will have a demand of 10, but then the item actually is only bought 5 times, then you have these 5 spare units that you have to store in a warehouse and you have to pay for that. But then, on the other hand, if you say the real demand will be 3, but the actual sales would be 5, you are losing this unrealized demand. So you are not getting the margin that the customers would pay you if they would buy this product for you. And depending on a specific market, depending on a specific use case, you might be having over-prediction that is more costly or under-prediction that is more costly. And you have to look at that from the very beginning of your modeling pipeline. So if you figure out this information, what you can actually do, you can incorporate this into the training loss of your model. So if you're using a deep learning model or a tree-based model, you can write down a custom loss that incorporates the information of the asymmetries or any other information about the loss, about the business KPI that you know. Because in that case, this is what the model will be optimized to do. And this will be the metric that the training algorithm will be targeting when finding the weights or finding the tree splits or whatever is the algorithm that you are using. For some algorithms, you cannot integrate the loss or you cannot update that and modify it manually. Still, what you can do is to use this business KPI to guide your model selection. So when you're training 5 models with different sizes, with different learning rates, with different features, and so on, you can use this business KPI to do the model selection, to do the parameter tuning, to basically select the one that optimizes your business KPI not the cross entropy, not some kind of statistical measure that you might have been using before, but the metric that incorporates this business relevant information. And even if you don't have access to the model selection stage, you can actually post-process the predictions in order to integrate some of this information afterwards. All right, so we looked at 3 lessons that would be useful in different projects. One other thing I wanted to talk about is a bonus lesson about the things that should not be learned from Kaggle. And I think many of you could potentially guess what I will be talking about, because if you enter one of the discussion forums and look at the competition results, you will often find pictures like that, where people discuss the solutions where they ensemble dozens or even hundreds of models with different weights, parameters, blend it, average it, stack it with some other models on top of that, and do a lot of heavy ensembling. This is not something that I would like you to take from Kaggle when working on your machine learning projects in practice. Not because it doesn't work, it still adds value, and usually the ensembles outperform single model-based solutions, but in practice, the additional effort that you need to implement this ensembles is not worth the potential accuracy gains that you can gain from that. So I wouldn't recommend you going for the ensembles straight away. I would recommend you focusing on the other lessons that I was talking about. So summing up, one thing I probably want for all of you to take away is not some specific lesson that I was talking about, but the thing that Kaggle is a very rich in terms of information and useful tips and lessons that you can find there. So if you go and start working on your ML project, whether it's work, whether it's research or something else, please go on Kaggle and see what are the similar competitions, what are the similar data sets that are available out there. I bet that you will find a lot of useful information which you can learn from, and some of the tricks that are specific to the use case that you will be looking at. And in case you want to read more, there are a couple of books that have very helpful information that you could also look at and get some more ideas about other tips and tricks that could be useful for you. That would be it in terms of what I wanted to talk about. Thanks a lot for your attention. Very happy to take any questions that you might have, or also take a more deep discussions after the talk in the networking zone. Thank you.
Thank you very much, Nikita. This was brilliant. So I think now it's time for questions. So if you want to ask some question, you can raise your hand and I will come to you and give you a microphone.
Yes, thank you for that talk. In your talk, you mentioned about post-processing predictions based on a business KPI, especially when you do not have, you cannot build customized losses or perhaps even tune hyperparameters to better incorporate the business KPIs. Can you talk a bit more about, can you perhaps explain a bit more about what do you mean by post-processing predictions? Thank you.
Yeah, thanks for the question. Very, very, very good point. When I talk about post-processing, there are a couple of things, a couple of aspects or dimensions you could look at. The first dimension is doing some simple changes to the predictions that may not be directly derived from the business KPI, but are still relevant for your business. So let's say in demand forecasting use case, what you can frequently observe is that sometimes models produce negative predictions. They would say, the predicted sale is -1. But you know that this is impossible, right? So the very first thing that you can do is to post-process predictions in the sense that you are removing the negative predictions and substituting them with 0. This will immediately improve your performance a little bit if you have such cases. And then another dimension is actually trying to integrate the KPI that you are targeting through the post-processing. So you could look at a couple of different optimization algorithms that as input would take the predictions produced by your model, and then as output would produce a processed prediction where the algorithm would optimize the business KPI that you are looking at. So basically, it's about writing the loss function not for the model, but for the post-processing algorithm, which is useful if you don't have access to the model and you cannot control how the model is trained. So same idea. Look at the business KPI, see whether there is an asymmetry or whether there is some further information that you can incorporate, and then maybe just you can use, for example, scikit-learn and some optimization algorithms from there and see whether you can optimize this objective function through a simple post-processing where you weight your prediction with specific weights.
Some more questions? Okay.
Hi, thank you for the talk. I have a very high-level question. Like, as someone who has spent a lot of time on Kaggle, how would you estimate like the gap between the academic, research and Kaggle? So, is there a place for immediately bringing in, the hottest state-of-the-art model? How do Kaggle datasets and competitions differ from academic benchmarks?
Yeah, that's a very good question. So I think if you look at that from the industry perspective, like what is more useful for me, academic experience or Kaggle experience when I go to a company and solve a problem there, I would say the combination of two is the best, but the Kaggle would give you more practical experience because when you go to Kaggle, there is no need to use one of these sound approaches, to use one of the established approaches. You can just go and see what is the most recent model that has been uploaded to GitHub. You would not need necessarily to see whether this model is performing good in the benchmarks or whether this model is, has been tested thoroughly in particular environments. You could just take the most recent artifacts, the most recent loss functions, the most recent model architectures, and this is what makes Kaggle really fast, because people really are taking the snippets from different places and then implementing them in the solution. And I would say that this is closer to how the industry works, because you don't necessarily need to use the solutions that have been established in the academia, which may take 1 or 2 years to become the case. So I would say that this is useful if you want to play around with more recent solutions. But then, on the other hand, when you want to learn about consequences of using these models, if you want to look at not only the model performance, but also look at things like how fair are predictions of my model, this is not something that you can learn on Kaggle. This is something that you can learn from papers or from additional research, and this is why you have to look at both sides of this coin. So my suggestion would be have a look at both. On the one hand, you have established methods from academia. On the other hand, you have methods that seem to work. Nobody knows why, but if they work, they still bring a lot of value. And then try to merge them into something that works well for your use case.
Thanks for the talk. So I have a question about the slide where you talked about you upsampled the image as the epochs progress.
Yeah.
Yeah. So is that the same model?
Exactly. So this, I'm just sliding down. Yes, this was the slide you were talking about. So some architectures in computer vision are agnostic of the image sizes. One example is efficient net models. This is a model family that is used frequently on Kaggle. But some other model architectures are specific to image sizes. In that case, you cannot really use that hack. You cannot really take a lot of advantage from that. But if you are using one of the model architectures that are image size agnostic, then the idea is to stick with the same model. To take, let's say we are taking an efficient net model and training it for 5 epochs with a size of 128, take those weights, change the data loader to now import the images of size 256 and train another 5 epochs. Then again, increase the image size, 5 more epochs, at some point they stop. This is the idea.
Cool. Yeah, I didn't know those models existed before. So it's not just like you're adding padding to the smaller images.
No,
Okay.
no. I think this is something you could try as well. Maybe you just fill so you are using the same image size, but you are filling padding the borders. But that would kind
Yeah,
of
that
eliminate
wouldn't-
the purpose
right.
of having still having the larger image that you have to import into your memory. So I think this lesson that I'm talking about here mostly applies to the cases where you use one of these image size, input size agnostic models.
Cool. Thanks.
Thanks so much for the talk. I have one question regarding the creativity of the grandmasters, for example. What were the most creative approaches to specific competitions that you've seen throughout the last 5 years that you've been doing those competitions?
Yeah, I think that's a very good question. So in my experience, when we are talking about tabular data, the most unexpected gains usually come not from using a sophisticated algorithm or not from using an ensemble that has 200 models, but through some kind of feature engineering. So basically what people are spending most time on is the creation of useful features to help the models distinguish, let's say, good risks from bad risks, or buying customers from non-buying customers, or something along that lines. So in tabular data, this really goes to the feature engineering and the creativity to come up with a certain feature that somehow uses the information from multiple features, but still provides some kind of new signal, provides sort of a dimension where it is easier to separate the classes. When we talk about unstructured data, this is where people are more creative in terms of coming up with novel architectures. So maybe, we are using a certain transformer architecture, but we actually add a couple of custom layers that are specific to this problem, but that can be very helpful for this specific use case. So I would say this is the areas where people invest a lot of time into, and where you, after a competition, you see, oh, this is what we did. That was a good idea.
Okay, I think we can have the last question. Yeah.
Compared to tabular data, how do you feel about tabular data that has a temporal structure? What kind of, or compared to, just not respecting necessarily the time series nature of the data, do you feel that's more difficult? Do you feel like, do we have the right tools for that right now?
Yeah. Sorry. Before you give out the mic, you talked about the panel data, right?
Yeah. So anything that has a temporal dimension.
Yes,
so like
exactly.
just basic time series or a graph that spreads over time or whatever.
Yeah. There is a couple of competitions that have the time dimension run on Kaggle. I think M4 and M5 forecasting challenges are ones of the most famous ones that some of you might have heard about them. I think that there is a lot of space here to explore, because what you notice in the more recent competitions is that usually the approach that the prize winners take is not using one of the modern deep learning architectures, but actually transforming the solution to a classification problem or regression problem where the lags of previous values of the time series simply serve as additional features. And this is how people usually reformulate the problem, when this is a classic regression or classification problem, and then we can use our tree-based models that tend to demonstrate the best performance here. But from the space of the algorithms that are designed specifically to do forecasting, I think there is a lot of further space to explore. Sometimes it is not as easy to set up some of these models, because incorporating this time component, especially if you also have static features and time-varying features, and you have a lot of entities and you have some hierarchical structure in your data, you have to really put a lot of time into untangling that on your own, and it's not easy to plug and play here. So I think that potentially in the future we will probably see much more interesting solutions to that problems. But as of now, the state-of-the-art approach that a lot of masters and grandmasters take seems to be, let's convert it to a classification or regression problem and work from there with manual feature engineering.
Thank you.
I think this was the last question, so now we can give a big applause to Nikita for this talk.